So in this video, we're going to solve the most difficult MCQs from March 2021, paper 12. So question number 3 says, substance Q is a hydrocarbon. When 1 gram of Q is completely burned, 3.22 grams of carbon dioxide is produced. What could be the identity of Q? Now, we know that Q is a hydrocarbon, so it has the formula CXHY. And we have to figure out this ratio, X is to Y. We need to figure out the molar ratio of carbon to hydrogen to first be able to determine the identity of the hydrocarbon. Now, they have given us combustion data. They've told us how much of the hydrocarbon we have, but we don't know the identity, and they've told us how much carbon dioxide is produced. So we can use that second piece of information. We know when we combust the hydrocarbon here, we get carbon dioxide and water. Now, obviously, this equation isn't balanced. But we also know that we have 3.22 grams of carbon dioxide. Now, how can we use this information? Well, if we know how much carbon dioxide we have, we know how much carbon we have. And all the carbon here comes from the hydrocarbon. So we can determine the mass of carbon present in 1 gram of Q. So let's solve for that. We know that 1 mole of carbon dioxide consists of 1 mole of carbon. In other words, every molecule of carbon dioxide has 1 atom of carbon. That means 44 grams has 12 grams of carbon. That's just the molar masses, which means that if I have 3.22 grams, what's the mass of carbon that I get? And if I solve for this, what I get is, so I can just cross multiply here, and I end up getting the mass of carbon as 0.878 grams. Now that means that the mass of hydrogen is simply the mass of the hydrocarbon, which is 1 gram, minus the mass of carbon. So we get 0.122 grams. So then we know that we have 0.878 grams of carbon and we have 0.122 grams of hydrogen. So we can figure out this is the mass ratio. So we need to figure out the molar ratio. So we divide by the relative atomic mass. So we divide by 12 for carbon. When we divide by 12 for carbon, we get 0.0732. We divide by 1 for hydrogen, we get 0.122. Then we need to figure out the simplest ratio because we need an integer ratio for the empirical formula. So what we're going to do is we're just going to divide by 0.0732. And we end up getting 1 is to 1.66. Now this is not an integer ratio. So all we can do is multiply by integers. If you multiply by 2, you get 2 is to 3.33. Still not an integer ratio. If you multiply by 3, you get approximately 3 is to 5. So that's your ratio of carbon to hydrogen. So we can say that substance Q is C3H5. That's the empirical formula. Now cyclohexene has the molecular formula C6H10 and the empirical formula C3H5. Cyclopentane is C5H10, which is CH2. Ethene is C2H4, the molecular formula, so the empirical is CH2. And pentane is C5H12. So that's the same as the empirical formula. So the only answer that works over here is part A, which is cyclohexene. Now the next question that we have is question number 27. Now this question says, in this question you can assume that hydrogen 1 and hydrogen 3 have the same chemical properties. There are 2 different isotopes of hydrogen. A sample of ethanol contains only 1 isotope, hydrogen 1, and it is reduced to compound Z in a nucleophilic addition reaction using NABH4. All the hydrogen atoms in NABH4 are the hydrogen 3 isotope. So this is the reduction of ethanol using the reducing agent NABH4 to form ethanol, right? We know aldehydes are reduced to primary alcohol. And compound Z, which is the primary alcohol, ethanol, is oxidized back to ethanol in water. Which statement about the final mixture of products is correct? So let's try to figure this out. What we have here is, initially what we have is a sample of ethanol that contains only the hydrogen 1 isotope, and it is reduced using NABH4. The equation for that is ethanol plus 2H, which represents the reducing agent. And we know that the reducing agent only has the hydrogen 3 isotope to form ethanol. Now, in the formation of ethanol, what we have over here is CH3, C, O, H, and now what we've done is we've added 2 hydrogens, right? So we have the hydrogen 3 isotope being added here, as well as the hydrogen 3 isotope being added here. So in our product, ethanol, we have two of these hydrogen 3 isotopes, two atoms of this particular isotope present. So now once we've made our product, which is ethanol over here, what we do is we oxidize the ethanol back into ethanal. And they want to know that which of your final products, ethanal and water, contain the hydrogen 3 isotope. So let's see what happens. So in the second equation, what we have is the oxidation of ethanol back to ethanal. So if we use O to represent the oxidizing agent, we're going to use O to represent the oxidizing agent. And now what we see here is, if you look at the next step here, what we have is, we have a carbon chain, right? So we have CH3, C, double bond O. We're reforming ethanal. And now if you notice, this oxygen atom here, the oxidizing agent, this oxygen atom takes away the hydrogen 3 isotope. It takes away the hydrogen 3 isotope from the OH group. So we know for a fact the water molecule will have at least one of the hydrogen 3 isotopes. And then it's equally likely that either of these two isotopes of hydrogen are removed. In other words, the final product can have the hydrogen 3 isotope, or it can have the hydrogen 1 isotope. Similarly, if you look at the water molecule, we already have one hydrogen 3 isotope, but we may have the other hydrogen atom may be a hydrogen 3 or a hydrogen 1. So 50% of the ethanol molecules will contain the hydrogen 3 isotope, whereas all of the water molecules will contain at least one hydrogen 3 isotope. So what we can say is that both ethanol and water will contain hydrogen 3 atoms in the final mixture of products. So A is our answer. All right, so the next question that we have is question number 32. And this question is on energetics. Now in this question, they've said an energy cycle for the combustion of methane is shown. So here methane is being combusted in its standard state, right, to form carbon dioxide and water in their standard states. So that's by definition the standard enthalpy of combustion. Now which expressions can be used to calculate the delta Hz? So what we're trying to say is which of these expressions is valid for this combustion. Now this over here is actually if we notice, this is the formation of the combustion products, right? Carbon dioxide and water are being formed from the elements in their standard state. But we have 1 mole of carbon dioxide and 2 moles of water being formed. Now, the first expression says that this can be seen as the delta H formation of methane plus the delta H combustion of methane. Now, if we look over here, what we have is the delta H formation of methane. The delta H formation of methane that they've shown, I'm going to highlight that with the green highlighter, right? Formation of methane plus combustion of methane is equal to delta Hz, which is in the yellow arrow. This is Hess's law, right? So we can either go from elements to the reactants and then to the products, or we can go directly from the elements to the products. So what we have over here is Hess's law. The green path is equivalent to the yellow path. The enthalpy change is independent of the pathway taken. So option 1 is correct. Now in the second option, they've said delta H combustion of carbon plus 2 times delta H combustion of hydrogen. Now, the combustion of carbon is the same as the formation of carbon dioxide. So over here what we have is, if you look at carbon to carbon dioxide, we have delta H combustion of carbon, because 1 mole of carbon is being combusted. And we have 2 moles of hydrogen being combusted to form 2 moles of water. So we have plus 2 times the delta H combustion of hydrogen. This is the same as saying formation of carbon dioxide or formation of water, or combustion of carbon is the same as formation of CO2. And formation of water is the same as combustion of hydrogen. And since we have 2 moles of that, we have this. So again, this expression is the same as the expression I've written down here. So this is also correct. So by default, we should know that the last expression is incorrect, because here we have the combustion of carbon plus the 2 times combustion of hydrogen. Here we have combustion of carbon monoxide plus 2 times combustion of hydrogen. Now again, if you notice, these two things are the same, that I've highlighted in yellow. We have 2 times delta H combustion of hydrogen, but we know that these two are not the same, right? Combustion of carbon is not the same as combustion of carbon monoxide. So we can already rule out option number 3, because these two values would be different. And if 2 is correct, then 3 has to be incorrect. So the answer is 1 and 2 are correct. So the answer is B. So the next question that we have here is question number 34. Question number 34 asks, which of these species can accept a lone pair of electrons to form a coordinate or a dative covalent bond? So which of these species can accept a lone pair of electrons to form a dative bond? Now let's examine these one by one. So if we look at option 1, we have BF3. Now we know BF3 is boron trifluoride. Now we know that fluorine has 7 outer electrons. So what that means is if I quickly draw the Lewis structure here, what we have is boron is forming a single bond with each of these fluorine atoms. And fluorine already had 7 electrons, right? So the 7th electron paired with the electron from boron. So now fluorine has complete octet over here. But what about boron? Well, boron over here is actually in group 13 of the periodic table. That means it only has 3 outer electrons. So even after bonding with each of these fluorine atoms, if you look at the number of electrons surrounding boron, now we have 2 plus 2 plus 2, which is 6. So it can still accept a pair of electrons to complete an octet. We know that period 2 elements such as boron can complete the octet. So what we have over here is that it can indeed accept a pair of electrons. So then we can say that one will be able to accept a pair of electrons. Now option 2, we just have H plus. Now H plus is when the hydrogen has actually lost this one outer electron that it had. So that means it has 0 electrons. So that means that H plus can indeed again accept a pair of electrons. And we see that, for example, when we form ammonium ions, right? From ammonia, for example, H plus accepts a pair of electrons from the ammonia molecule. So we can say that H plus will also accept a pair of electrons. Well, what about CH3 plus? Well, with CH3 plus, what we had was carbon had 4 outer electrons. 3 of them are bonded with hydrogen. And the fourth one is no longer present on the carbon atom, right? That's what gives it the positive charge. So that means, again, the CH3, the carbon has 6 outer electrons. So it can accept 2 more electrons. And that's what we're going to see. So we're going to see that CH3 plus can also accept a lone pair of electrons. And we see this happening in reactions such as, for example, in electrophilic addition, when we have a carbocation, right? In the second step of the reaction, the negatively charged species donates a pair of electrons to form a bond with the central carbon on the carbocation. So we can say that all 3 will be able to accept a lone pair of electrons. So the answer is A. The next question that we have over here is question number 35. Question number 35 says, a sample containing X moles of aluminum chloride is dissolved in water to give solution W. In order to precipitate all of the aluminum as its hydroxide, Y moles of sodium hydroxide are required. More of the alkali is added then to redissolve that precipitate, giving solution Z. Which statements are correct? The initial pH of solution W is below 7. Well, we know that this is true because we've learned this in period 3, that when Al2Cl6 is dissolved in water, it's hydrolyzed. It can be hydrolyzed by water, resulting in an acidic solution. So we know that aluminum chloride forms an acidic solution in water. So we can say that solution W is an acidic solution. This is an acidic solution. So therefore, the pH is below 7. And the second part, what they say is that Y is equal to 3x. So what that means is that the number of moles of sodium hydroxide is 3 times the number of moles of aluminum chloride. In other words, if I have X moles of aluminum chloride, I'm going to need 3 times that number of moles to precipitate that aluminum chloride entirely. So let's construct an equation. If I have Al2Cl6 reacting with sodium hydroxide, what I form is the hydroxide, which is the precipitate here, so AlOH3 thrice, plus I have NaCl, so that's the salt. Now, if we balance this equation, well, we have 2 aluminums here, so we're going to need 2 AlOH3 over here. Now we have 6 hydroxides here, so we're going to need 6 of these NaOHs. And now if you notice, we have 6 Nas and 6 Cls. So that means we're going to have 6 NaCl. So this is the balanced equation. Now what that means is that if I have X moles of aluminum chloride and Y moles of NaOH, Y must be 6 times the number of moles of aluminum chloride. For every mole of aluminum chloride, I need 6 moles of sodium hydroxide. So we can say that y is equal to 6x. So we know that y is not equal to 3x. So now that we know that statement 1 is correct and statement 2 is incorrect, we know that the answer must be D. Now we already know the answer, but let's just examine statement 3. Now statement 3 says, now what we have in solution Z is that solution Z is formed when more alkali is added to dissolve the precipitate. So here we have a precipitate. And when we add more sodium hydroxide, what we have over here is that we form this guy over here, NaAlOH times 4. So this over here is the AlOH4 is a complex or is a compound anion, and we have Na plus over here. So this guy is soluble in water. Now, does Z contain X moles of aluminum? Well, let's see. This is your solution Z. Now, we know for a fact that for every X moles of aluminum chloride, we're going to have 2X moles of aluminum hydroxide. We know this from the ratio 1:2. So that means that if we have 2X moles over here, we have 2X moles of this guy. And every mole of this has 1 mole of aluminum. Therefore, 2X moles of this will have 2X moles of aluminum. So the final solution Z actually contains 2X moles of aluminum. So we know that statement 3 is also incorrect.